started. We are still on this section. Hopefully we'll get it finished today, although there's an awful lot of work in it, so we might not. We're going to move from finding local max and mins to finding absolute maximum and minimums when there are constraints typically. There are only 3 of these questions that kind of fall into this category, and I think there's another 3 that fall into the second version of this. So the first version is when the constraints are linear. In other words, you can only pick values of x and y from a shape like a triangle or a rectangle, or in general, just some kind of polygon. And this is kind of how you would do it. You find the critical numbers in the usual way, and you check that you're allowed to use them. Can you imagine that you might have a critical number, but it's not in the restricted region, right? Because you're basically going to get a question like, find the absolute max and min of f of x, y, but it has to be in this rectangle, right? You can only choose from this constraint. And so you find your critical numbers, and you might find out that some or none of them can't be used. So you only keep the ones you can be used. You then find the corners of the polygon, and you evaluate the function at that. And whatever is the largest answer out of these is your absolute max, and whatever is the smallest out of these is your absolute min. So pretty straightforward. Actually, an awful lot less work on the algebra side, because really all you need to do is find the critical numbers, right? So you don't need to find fxx and fxy and d and all that stuff. You don't need to do that. All you need to do is find the critical numbers. So here is the example I'm going to do to kind of show you that. And this example basically will follow this. And 12, 13, and 14 fall into this category. So imagine I want to find the absolute maximum and minimum of this polynomial function. And the region D, the constraint region, is the region that makes a triangle, and it's from 0, 0 to 0, 2, and 10, 0. So because I'm a visual person, I like to draw what the restriction is. And in this case, take a few seconds to find the right color pen. Here we go. Making no great attempt to be accurate. So can you imagine that the region that we are interested in is that we can only pick x and y values that are in that triangle or on the edges of that triangle. So that's what that question is saying. What's the largest and smallest value of this function when you can only pick numbers in this triangle? So step 1, find the critical numbers. So the partial derivative with respect to x is 2x take away, well, that's nothing, and 2y, and I set that equal to 0. And then I do the partial derivative with respect to y, and that becomes 1. That's nothing, that's 1. And with respect to y, that becomes negative 2x equals 0. And now we've got a system of equations, and we, there are all sorts of combinations here, but you try and make life easy. And would you agree that this equation here is very easy to solve? In fact, won't that work when x is a half? Agreed? So x has to be a half. Now, if I put x equals a half into equation 1, we get 2x take away 2y has to be 0. 2 times a half take away 2y has to be 0. So far, so good. And since I'm running short of room, can I just say y equals a half? So in this story, isn't there only one critical number? It's the point 1/2, comma 1/2. Now I should check that that's in that region. And I know I have a horrible scale, right? But would you agree a half, comma half is probably there? Would you agree it's safely inside the triangle? I'm not proving it, but I can look at it and tell. Now, if my critical number was 20,4, right, just in a different world, would you agree 20,4 is not inside the restricted region D, And that means don't use it. Don't even put it in your calculation. Throw it away, it's gone. And can you imagine you might get 1 point in the region and 1 point out the region? If that happens, only choose the ones that are in the region. So right now, we have got one critical number at a half comma half. Find the coordinates of the corner of the polygon and evaluate f of x, y at that. So in this case here, I'm going to do the whole thing in one go. Here are the places where we're going to look for the absolute max and min. And we're going to evaluate it, which is this guy, at all those places. One of the places is the critical number, which is that guy. And the others are the corner of this triangle, 0, 0, 0, 2, and 10, 0. And there's a lovely little theorem, which I'm just doing without really saying it, which says if your region is made up of straight lines, you only need to look at the corners. You don't need to look at all the points along the straight line. I looked at WebAssign and they did it the hard way. They actually looked at all the points along the straight line. You don't need to. Now, if you plug in half a half here, the value of the function at that point will be 1/2 squared plus a half, take away 2 lots of 1/2 times another 1/2. So that gets me a quarter, so 0.25. The value of the function at 0, 0 is dead easy, it's 0. The value of the function at 0, 2, well, that's nothing, that's none, so you get 2. And finally, the value of the function at 10, 0, that's 100, nothing, nothing, so you get 100. Now you're pretty much finished. The question was, what is the absolute maximum value of this function? And what is the absolute minimum value of this function, subject to this constraint? Well, the absolute maximum is 100. Would you agree that's the biggest answer out of the 4? And the absolute minimum is, in this case, 0. You agree it's a little bit easier to do than the local max and min because of all the algebra stuff you have to do and the FXX stuff. So a little bit quicker because of that.
You just made my heart freeze though when you talked about checking every point along a line, because if you're talking about a curve, that's an awful lot of points.
Yes, but we're actually going to do all the points along the curve and show you that there's a sneaky way of getting around that problem, that there's an awful lot of points.
Good.
But we'll wait till we hit that question. Right now we're doing polygons, right? Any shape that's made up of nothing but straight lines called a polygon. Are we comfortable with the process? How we did this? Yep. Do you want to see one more of these, or can we call this one good?
I'd appreciate seeing one more.
Okay, so let me pick one. I like to pick ones that come from the homework because the chances are that they're going to be nicer than the ones I would get if I just made them up off the top of my head. By the way, I made that one up off the top of my head. Okay, where's 264? Here we are. Max and min, here we go. So 12. Okay, try 13 maybe. Yeah, okay. So in this next example, is going to be similar to question 13. The function that we're going to deal with is a polynomial function, x squared plus y squared plus x squared y plus 9. And the region is all the points in 2D space such that the absolute value is less than or equal to 1, and the absolute value of y is less than or equal to 1. Okay, so again, I draw this. It's helpful if I draw a picture, because when I get a critical number, isn't it easier to go to the picture and say, yeah, it's inside or no, it's not, than to try and find out if a particular critical number is or isn't in it. Now, if you choose a value of x where the absolute value is less than or equal to 1, you get those guys. And if you do have y, you get there and there. And so the region is actually a big square. that looks something like that. Are you happy about that being region D? Are we good?
Yep.
Right. So I'm really only interested, and I might as well do them right now, in the corners. Is that going to be? There we go. Right, so let's do the math now. I have my function. I need to find its partial derivative with respect to x and set it to 0. And partial derivative of y. And here is our two equations. And you just have to take what you've got and go with it. There's no one unique way to solve these because it depends on what the two equations look like, how you're going to deal with it.
For the partial derivative of y, wouldn't that just be x squared?
Oh,
y plus x squared.
X squared. Agreed. It's good when you get the question right. I didn't interpret it right. Right. So we got an x squared. Are we good? Now that one is 2xy. That's good, right? So give me any method you can think of that you might use to find the critical numbers. I can think of one right now, and if I thought hard enough, I probably could think of another one, but I can think of one right now. Okay, I'll give you a clue. I'm going to look at equation 2.
So we solve that for y.
Okay. I'll be cool with solving for y. Basically, I'm going to do a substitution technique. So I now am going to put y equals -1/2 squared into equation 1. So instead of 2x plus 2xy equals 0, I'm now going to have 2x plus 2x times -1/2 x squared equals 0. And that's going to be 2x take away x cubed equals 0. And I'm going to pull out an x, and we're going to have that. So far, so good. That gives me x equals 0. And this one here gives me x equals -square root of 2 and x equals +square root of 2. And I'm going to kill those two right now. I'm not even going to use them. What's the problem with these two guys? These two possible critical numbers that I could use?
With the positive and negative square root 2, would that be outside of the domain?
Yeah, they'd be over here somewhere. So remember, when you're looking for absolute values, you're only interested in critical numbers that are in here, right? Would you agree x equals 0 at least has got a fighting chance of being in here, as long as its y value is, not bigger than 1 or -1. So since I only have one x, can't I then find out what the y value is by using it in this? And guess what? Maybe not the most interesting point in the world, but isn't 0, 0 a critical number? So far, so good. Right, now I've got everything I need, so I'm just going to set up my table. And at the critical number, which is 0, 0, I'm going to find the value of the function. I'm also going to find it at all these points. Doesn't matter what order you write them in, as long as you write them down. And whatever one of these is the biggest, won't that be my absolute max? And whichever one of these is my smallest, that will be my absolute min. So here goes. If you plug in 0, 0, 0, 0, oh, you get easy. If you plug in 0, 0, you get the answer 9. If you make x -1 and y +1, you get 2, 3. Let's check that. That's 1. That's 1. Y is 1. That's 1, so you'll get 12. Negative, negative, total. Would you get 1, 2? Take away 1 is 1 or 2. I believe you get 10. If you plug in 1, 1, you get 12. And if you plug in 1, negative 1, you get 1, 1. Take away 1. So you get 10 again. Hopefully I did them right. Well, the smallest answer is 9. And that is our absolute minimum value for this function under those constraints. The largest answer I got, and the fact there's 2 of them doesn't matter, is 12. So I'm saying the absolute maximum is 12. So when you get your answer, you will simply just have 2 boxes, something like this. Absolute minimum, put in a 9 there. Absolute maximum. We don't care that it happens twice, we just need to know that it happened. And that would be what your final answer would look like. Would you see it? It's really not, you don't write a lot in the answer, right? Isn't getting the answer takes a fair amount of work, but what you write down is very minimal.
Thank you.
Right, and we cool with this process now. So I could do any old polygon in the world, literally, couldn't I? And, you know, 1, 3, 7, 9, 22, 4, 18, 11, and then a couple of critical numbers and off you go. Just make sure that when you have your critical numbers, that they fall inside the region. If any of them are outside, like 2 of these were, don't use them. Because if you plug them in, couldn't you well get an answer that's not usable, and therefore you'd think the maximum is 22, but you couldn't use that number, so it can't be 22. So far, so good. Let's look at how you do it then when the region has a curve in it, in particular, a circle. So the one I'm going to choose is a version of question 14. There's no way in the world I'm going to make up my own, because you would get really weird numbers if I tried. Not the ugliest looking function in the world. The region D is described as all the points x, y. That vertical line is the words such that. X is greater than or equal to 0. Y is greater than or equal to 0. And for good measure, x squared plus y squared is less than or equal to 3. Right, now I'm going to try and draw that guy. Although it looks messy, isn't it basically this guy? Does that make sense? It's the piece inside the circle. Now, what radius is that circle?
3.
No. What radius is that circle? Think again.
Yeah, radius would be the square root of 3.
Yeah. It's easy, you know, if that was 9, then it would be 3, right? Now, would you agree that we have some corners here, here, and here? And would you agree that the new guy in town is, what do you do if at least one side of the shape is a curve, right? In this case, it's a circle, right? And I'm going to show you how you do that. And the first part is find the critical numbers and check if they're inside this region. So let's do that. If you differentiate this with respect to x, you get y squared. Not very interesting. If you do it with y, you get 2xy. Oh, come on, they could have made life hard. I know the answer to that without even doing any algebra at all. Isn't there only one combination that's going to work for those 2 equations? What's the critical number? Critical coordinate.
Is the critical number the origin 0, 0?
Would you agree that's the only way to work? If y squared is 0, doesn't that make y 0? If you plug y 0 into the second one, doesn't that make, well, technically, I guess you could say it makes x anything it likes. But the other choice here isn't that x has to be 0 anyway, so I know it's the origin, right? So x has to be 0 and y has to be 0 if we're going to make this work, which is not really very interesting because isn't it one of the corners? So I don't need to look at that guy. Or I do need to look at him, but I don't need to worry about it. Now let's deal with this curve. The curve is basically, oops, all the points where that is true. And would you agree that there's an infinite number of points? So I can't just find them all and check them. So how do I get around that? Well, it's a bit sneaky, but choose one of the two variables. In this case, it really doesn't matter. Do you want me to do X or Y? It really doesn't matter. Well, actually, I kind of does now. I'm looking at it just for algebra reasons. Okay, I won't give you the question then. I am going to rewrite Y as 3 minus X squared. Would you agree that's true? And then you go to your original function and you will say, this guy, when Y squared is that, becomes this guy. So all the points in that curve have the function that they're equal to this. See, a little bit sneaky? Basically, you take one of the variables out of the board. Now, could I have called that Y equals the square root of 3 minus X squared? Sure, but wouldn't you still end up with that? If I'd went the other road, would you agree it would be a much uglier looking function if I did it, you know, in terms of Y? And that's kind of why I chose it. Now, I'm going to do a little bit of math on this. Now, what are we looking for? We are looking for essentially, it's like critical numbers, aren't we? We're looking for places where this would be a max or a min. Where do you find maximums and minimums from Calc 1? Where do maximums and minimums live?
Where you have a slope of 0 or a slope of undefined.
We'll go for zeros. Technically, yes, you're right, we undefined, but they don't give you questions that use it, so I'm just going to pretend they're not there. Isn't it when the derivative is 0, this function will reach its max or min? So if you differentiate with respect to x, I believe you get that. And if you set it to 0, then 9x squared equals 3. So x squared equals a third. And so x will be plus the square root of 1/3. And the other one would be negative the square root of 1/3. Let's do the x equals positive the square root of 1/3. Let's make it look pretty. Can I just call it 1 over root 3? I know I could make it prettier, but that's better than nothing, right? And that guy, we then have to find what the y coordinate would be. Well, essentially the y coordinate is the value of this function. And so it's going to be 3 lots of the x guy, take away 3 lots of the x guy cubed, add 9. And so that's going to be 3 over root 3, take away 1 over root 3, add 9. So I make that 9, add 2 over root 3. And that is very worrying because I've screwed up. Because I used the wrong function, didn't I? Let's fix it.
You put it through. Oh, wait.
That's the one I should have used, isn't it? And so we have an x value of 1 over root 3 squared plus y squared equals 3. So that's 1/3 plus y squared equals 3. So that makes y squared 8/3. And that makes y plus the square root of 8/3. And y equals negative the square root of 8/3. Which I'm now going to call, God, there's no way of making that pretty. Oh, let's just leave it alone. We're going to calculate it in a minute anyway. So that means that we have to look at a number of possible points. And the x value we have is 1 over root 3. And the y values are that guy, that guy, that guy, and finally I should have had the minus, there we go, and finally this guy. We've got all combinations, I do, right? Sorry about the mess. These are people on the curve. Now, somewhere in my picture, I've got these guys. There's 4 possible candidates. How many of them live on that curve? Because they don't all live on that curve. Would you agree any point in that curve, the x and y are both positive? So it doesn't not.
The first one, because that's the only one that's exclusive. That's in the first quadrant, which is where our domain is.
Yeah. So you agree that the only one you keep is that one. Which means that after all that hard work, we have got a number of places to go hunting for the absolute max and the absolute min. And this time, it's f of xy. I have the origin, that corner, this corner, and that ugly guy. So there are 4 possible places for the absolute max and the absolute min to live, right? So 0, 0 gets me 9. That's pretty big. 0 root 3, what will that get me? That'll get me 0 times that, doesn't really matter, because it's going to get me 9. Root 3 times 0 really doesn't matter because it's going to get me 9. Not an awful lot of variation here, right? So that guy better be something that's not 9, because that would really worry me. So I'm going to find the value of the function at 1 over root 3, that fella. And so it's going to be x times, this is going to come out a little bit nicer, squared plus 9. That's 1 times 8 is 8. That's really the square root of 3 times 3, so I guess it's 3 root 3 add 9. And I'm giving up on trying to make that a perfect answer. So 8 divided by 3 times the square root of 3 plus 9 is roughly 9.56. Isn't that my absolute maximum? And these are the absolute minimums. Right, the process is correct, but you know, you might go.
I got 10.54 approximately.
Okay, so it might be 10.54. It'll still be the max. So the process is correct. This is for you to check on your own time. If somewhere earlier on I screwed up with the algebra, will you still think the process and not get too caught up on the details? So I think we need another one of those curvy ones, don't we? That one was trickier. So I was hoping that that one would come out nice, but evidently I screwed up in the numbers, but that's, or the choice of numbers. Which one? This one or this one? Do I want this one or this one? No, I want this one. So we've got a function, 2x cubed plus y to the 4 plus 9. And the region D, the constraint, is a set of points xy such that x squared plus y squared is less than or equal to 1. So that's a pretty simple picture. Would you agree it's just everybody inside a unit circle? Are we good with that? Now, there are no corners to this shape. Isn't there just one big curve, right? So we're just going to have to deal with that. But before we do that, let's find potential critical numbers. I got 6x squared. Well, that was boring. And I got 4y cubed. And that was equally boring. Would you agree that there's a no-brainer going on here again? What is the only combination that that's true for? What's the critical number?
Again, the origin.
And would you agree that is safely inside the region? Right. Now, these points that I'm now, you know, pointing my finger at, right? These guys here, they are not corners. So don't write down 0, 1, 1, 0, and all the other combinations. That's an extra one, by the way. You'll just add extra work and you won't get an answer, unless by sheer fluke it happens to be one of the places that you want to look. So what we now have is to deal with our function, which is this guy, and change it so that it only uses one variable, using the fact that the boundary of the circle is that. Now, I can take this equation and rewrite it in two ways. I could say that y squared was 1 minus x squared, or if you really wanted to be weird about it, you could write that. Or I could write it as that. And I'm going to look at the original equation here. And I'm going to say to myself, which one of these two options is likely to give me the nicest algebra? Because I don't want to make my life hard. Should I use the y squared equals 1 minus x squared? Or should I use the x squared equals 1 minus y squared? And remember, you're going to be plugging in here. Which one? The y using x's, right? So I'd replace the y's with x's, or do I replace the x's with y's? Yeah, 50-50 chance, I guess.
Use the y.
X is with y.
I know you said something, but it just died. I couldn't hear it.
X with y.
Okay, so you're saying you're going to use this one, or do you mean this one? I'm not sure what you mean.
The bottom.
Yeah, okay. Let me tell you why I'm going to use the opposite. It's 50-50. That's the original. Isn't y to the 4 just y squared squared? Would you agree that algebraically, that's not too bad? Right? Would you agree that'll foil out and it will be reasonably nice looking? Right? Reasonable. I won't say it's perfect, but it's something. If I went the other way, right, which I could have said, okay, I'm going to go g of y, right? And so it would be 2x cubed plus y to the 4. If I write this down, it's going to be 2 times the square root of 1 minus y squared cubed plus y to the 4. Right. From that one or that one, would you agree that that one is much uglier to differentiate and deal with? Would you agree? So that's why I chose that. Now, would it work with this? Sure it would. You just give yourself twice as much work to solve it. So that was the argument that I would do. I'm going to make this a little bit prettier. So I guess the rules of the story here are try and avoid square roots and things. That ends up being, I believe, that guy. So I need to find when its derivative is 0, because that's going to tell me the points on this thing that are worth looking at. So the derivative is 6x squared, take away 4x, plus 4x cubed, and I'm trying to find out when that is 0. And I'm a picture straightener, so I'm going to call it 4x cubed plus 6x squared minus 4x. That's not a big deal. Right, what could I do next to try and solve this equation to find the numbers on the outside that are useful to look at?
You could factor out a 2x.
Okay, and that would leave me with 2x squared plus 3x minus 2, I believe. Agreed? Can you factor that guy? Yes, you can, is the answer. Can anyone tell me what the factors should be?
Two x minus 1, x plus 2.
Nailed it. Which means that we have x equals 0, x equals 1/2, and x equals -2. Before I continue, why am I killing that one?
Because it is less than -1. And so
Yeah.
that's it.
You're going to find when you do this algebra that there are going to be candidates that are not usable, right? So it's always handy to have that picture handy, right? Because that is a solution to when is this function have a 0 derivative. It is not always going to tell me every value I should use, right? Some of them won't be usable. Suppose I had another answer, x is 50. Wouldn't I throw that one out as well? It has to be on this region here, right? Now, if x is 0, can't I get the y value, right? If I know what x is by using this guy. So I've got my pen. So I have, when x equals 0, I know that x squared plus y squared is 1. That gives me 0 plus y squared equals 1. Can I cut to the chase and say plus or minus 1? So that means 0, 1, and 0, -1, which is actually more by coincidence than design, is it not? Those two guys there. Oh, and by the way, there's our critical number, so we've got 3 points. If I then try x equals 1/2, so when x equals 1/2, let's see what the corresponding y value on the circumference of the circle will be. It will be 1/2 squared plus y squared is 1. This is easy to do, it's just time consuming. So it's going to be plus the square root of 3/4, and the other choice is negative the square root of 3/4. I'm pretty sure those numbers work, so I'm going to use them. And so that means that we now have, here's our xy, and here's going to be our function. We now have the origin, which was the critical number. We have a 0, 1, and we have a 0, -1. We just found them here. And we have a 1/2, that guy. And lastly, 1/2, that guy. And for every single one of those points, won't we now evaluate the original function?
I can't see the entire table.
Does that help? You see it now? Yes, no,
I
maybe?
think so there isn't anything below the. Oh, yep, I see it now. Thank you.
Okay. So for every one of these points, we evaluate this function. I'm going to make no attempt to do it. I'm just going to lie and write down random answers. That is 9, that is 7, that is 7, this is 14, this is -14, right? Just random digits. But if that was the true answers, wouldn't we then say this guy here is the absolute minimum? And wouldn't we pick that one as our absolute maximum?
Actually, when you pick the positive 14 for your absolute
Oh,
maximum,
absolute maximum. Okay, I'm going to change this to 90 so I don't need to change my answer. Right. But you're right. I should have said positive 14. So the biggest answer is your absolute max and your smallest answer is your absolute min. So we'll pretend that says 90. You see how that process is going to work? Normally when you get curves, it's circles. And because it's circles, you do what we did here. And be on the lookout for guys that don't work, right? Because sometimes you don't even bother checking, you put it in the table, and the guy that we kicked out might have gave the answer 82, right, or something, right? And that might alter what you might then not have the real answer to the absolute max and min, right? You'd have some answer that was never usable in the first place. Okay, that's as much as I want to do with those guys. They are very long to do. And for the time we've got left, I want to do a quick puzzle one. If I can find it, there's a good puzzle one in here. Right. Here it goes. Find 3 positive numbers that, that have a sum of 60, right? And whose product is a maximum. And you might think that this puzzle is impossible because there's not enough information, but there actually is. So in the next few minutes, let's show you. I'm going to make X the first number. I'm going to call Y the second number. And I'm going to call Z third number. Since you tell me that the 3 positive numbers have a sum of 60, the constraint here is that X plus Y plus Z have to equal 60, right? That's my constraint. So far, so good. Now, you're being asked to maximize the product. So imagine I have a function, and I'm going to call it f of xy, and the product is x times y times z. And you might say, wait a minute, there's 3 variables here. You should have called that fx comma y comma z. But watch what I'm about to do. Where did that 60 take away x, take away y come from?
From the x plus y plus z equals 60.
Yeah. Would you agree that if x plus y plus z equals 60, then doesn't that mean z has to always be 60, take away x, take away y? So do you see how I've reduced the variables? Now, if I multiply that out just to make things a little bit more tidy mathematically, here is the function that we are trying to find the maximum for. Now, here's the good news. There's only one maximum, right? That's why it's called the maximum number, right? It might happen in 2 places, but there's only one maximum. So don't I just need to find the critical number? Because isn't that the only place the maximum can live, right? Because there are no more constraints, right? And so we need to solve when is 60y take away 2xy minus y squared equal to 0. And if I do this other one with respect to y, you get 60x with respect to y x squared, and respect to y minus 2xy equals 0. And so if I can solve an x and a y where these are both true at the same time, haven't I found the value for x and y that gives you the maximum product? Because there's only one answer, it must be the answer that we're looking for. I've run out of time here. So while you're typing in your last name, has anybody got any ideas of how you would solve this particular question?
Can you factor the second one?
This one here. You can
I think
factor
you
out.
might be able to pull out an X. I can
Yeah.
definitely pull out an X. The top one you can pull out a Y,
Okay.
and then
Keep that thought process. It's a good one. Okay. So that guy has to be 0. That guy has to be 0. Would you agree one of the possibilities is X equals 0, Y
Y
equals
equals
0,
0. Yeah, that is a definite possibility.
right? So I'll put that down as one of the choices. Obviously, the one that gives us the biggest answer is a maximum. That one there actually would get you probably the smallest answer, because wouldn't it be 0 times 0 times 60, which is 0? Would you agree that's a pretty small
Yeah,
answer?
it'd be 0.
Right. But if you suck out what's left, you have 60 take away 2x, take away y has to be 0. And you've got 60 take away x, take away 2y has to be 0. Don't you have a system of equations that you can solve for x and y?
I mean, I don't know if I can solve them, but somebody probably
Oh,
could.
everybody can solve them. You just have to rearrange it, right? I know this isn't true, but can we pretend that it was 20 and that y is 20, just for argument's sake, right? Then wouldn't the maximum value be x is 20, y is 20? So that makes z 20. And so 20 times 20 times 20 would be the maximum product. And that's how we would finish that. We'll probably do that tomorrow to finish off, right? Are we good? So a nice little puzzle one to finish. We learned some cool stuff today. See you tomorrow.